We are like really on a very ambitious mission to revolutionize this development of these adaptive intelligence agents by building a software engine that streamlines the entire process. The thing is that these agents that rely on the first principles AI, if you were to build them from scratch, you would have to endure tedious calculus and very challenging programming. And this makes prototyping and development time consuming and prone to errors. And to tackle this problem, we first developed this open source toolbox called Reactive, which consolidated many years of research and engineering. And then we said, okay, we see that there's quite some interest growing in the field of first principles AI because, well, the generative AI and other, let's say, purely deep learning based methods, they aren't meeting the requirements, the systems that must operate in the uncertain environments. And then we said, how about we take this Reactive and make it Reactive Pro by basically making a professional toolbox that would streamline this development.
In this episode, Albert recounts his journey from Lakota, Russia, to his passion for computer science. He describes his academic trajectory from studying at St. Petersburg to earning scholarship and master programs in Kyoto, Japan. There, he focused on developing driving aids for elderly drivers, but faced challenges with system performances, leading him to pursue a PhD in Bayesian inference. Albert explains Bayesian inference as a method for updating beliefs about uncertain quantities based on new evidence. He discusses its applications in addressing uncertainty in complex systems like personalized hearing aids. The conversation touches on the differences between Bayesian AI and reinforcement learning. Albert also introduces RxInfer, an open source toolbox programmed in Julia, designed to automate Bayesian inference through reactive message parsing. He emphasizes RxInfer's efficiency in handling computational resources by processing information only when necessary. Welcome to Inspiring Computing. This podcast is where computing meets the real world. Inspiring Computing aims to trigger your curiosity by talking to proficient and advanced MATLAB, Python, and Julia users who use these tools to deepen their understanding of the world around them by simulating it, exploring trade-offs, and gaining insights that help their companies add more value. In addition to proficient users, we will be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives their development and what issues they're solving for others to benefit from.
Hi, Garrett. It's a pleasure to be here.
I've been looking at your profile because you're actually quite active in the Julia community, and I saw you at a local conference with this cool company called Lazy Dynamics, and you spiked my curiosity, and I had to have you on Inspiring Computing. But before we go into too much about your company and what that's all about, can you maybe tell me a little bit about yourself?
Sure. Originally, I hail from it's a city in the far east of Russia, which is about, I've just checked in the morning, 400 kilometers away from the North Korea border. So it's pretty far from here. I basically found my passion in computer science when I was in a junior high school. And by the time I finished the school, I made my mind that I want to excel in it. So it was time to pick up the university. And thanks to my score at the Unified State exam, I managed to secure the scholarship at St. Petersburg State University, which was 9,000 kilometers away to the west. Yeah, and I basically enrolled in the Faculty of Applied Mathematics and Control Processes on the bachelor track, which was called something like Applied Mathematics, Computer Science, and Programming. So that was the name of the track. And the naming of the track was really reflected in the priorities because it was heavy on math rather than coding. But I persevered and eventually graduated with honors. And then my journey took, I would say, an exciting turn. I earned the scholarship from a Japanese Ministry of Education for the Masters in Computer Science at Doshishu University in Kyoto. And there I had the pleasure to work under the guidance of Professor Ivan Tanev, and where I basically focused on developing the driving aids for elderly drivers. So the project I was focusing on it involved the creating of the system that could anticipate when a human driver wants to or intends to apply the emergency braking before they actually hit the pedal. It was pretty fun, actually, because I had this full-scale driving simulator. I collected the data and ran experiments. It led to a few publications and a patent, but however, and this is where actually the story starts with me going into PhD, because I figured out at some point that the performance of that system, it fell short when I was testing it on the new drivers. There were like so many frustrating false positives. So you can imagine if you're driving the car, right, and then at some point the system thinks that you're applying emergency braking, but you actually didn't want to do that. That can be really annoying. So I was actually determined to refine my approach, and that's how I stumbled upon Bayesian inference, which kind of was the main topic of my PhD at TV. So basically that idea of Bayesian inference, it offered the solution for this in-the-field learnings. Yeah, and my former supervisor basically encouraged me to pursue the PhD, and I considered a few options and found that the most intriguing opportunity at Bioslab, which is a part of Eindhoven University of Technology, and that led where I am now in the Netherlands.
Wow, so you've got this kind of superhero story of going to St. Petersburg, and then you went to Japan, and now the Netherlands, right? And currently you are the CEO of a company called Lazy Dynamics. Just from my understanding, what does actually Lazy Dynamics do?
That's a very good question. So Lazy Dynamics is basically a spin out from Bioslab, or a startup which started with our friends from Bioslab. And basically, Lazy Dynamics has a very ambitious mission. The company tries to streamline the development of intelligent agents that are resting upon emerging technologies such as first principles AI and Bayesian reactive inference.
I need to double click on. Maybe
Right.
not
Yeah,
all
yeah.
mortals on the planet know what Bayesian inference is. Can you explain this to me? What it actually is it? And maybe to ground it, a concrete example of why
Sure.
this is actually such a powerful technology.
I think it is better before we actually jump into Lazy Dynamics. Let me unroll a few things, right? Why did I actually go for this Bayesian inference at first place? Basically, so as I said, I stumbled upon this problem, right? There were like many false positives for the new drivers during my master's, like when I was exploring these driving aids. And then I found this Bayesian inference. And essentially what Bayesian inference is the method of updating beliefs about uncertain quantities based on the new evidence. So and the process of doing so is called inference, right? And by applying the Bayes rule, we can essentially update the certainty of our classifier. So Bayesian inference, it rests upon 4 important quantities, and I will just explain to you and try to link it to the problem which I faced. First of all, there are 4 core concepts in Bayesian inference. It's a prior distribution, and that basically represents your initial belief about the situation based on what you know before seeing any new data. So for example, if you believe that the most drivers abruptly release the accelerator pedal before applying the emergency braking based on your experience or some general knowledge, that's your prior. Right? Then there is another notion is a likelihood. And likelihood is also very important because it indicates how probable it is to observe your actual data given various possible scenarios. For instance, again, if we consider this driving aid, if your scenario is the driver applies the emergency braking, the likelihood would basically be the probability of observing the emergency braking if the driver had dropped the accelerator pedal too fast. So that's the likelihood. The last important thing in this Bayes rule and Bayesian inference is evidence. Mm-hmm. And the evidence is basically the probability of observing this data under all possible scenarios, taking into account how likely each scenario is. And it's essentially a normalization factor that helps to adjust your beliefs based on the observed data. So for example, it represents the overall likelihood of seeing emergency braking among all drivers, among all behaviors. So whether they intended to do so or not. And so given all these 3 things, you have prior, you have likelihood, and then you also have an evidence, and they basically give you something called posterior distribution, which is basically update of your initial guess, your prior, in the light of new data. So that's easy as that. And actually in the Bayesian inference, everyone is just hunting this posterior distribution.
So maybe just to make sure that I'm following you here completely.
Yeah.
So usually in a control system or a complicated system, you always have, it feels like designers think of things very specifically. You have requirements to say that, okay, a car shall have to brake under these conditions, right? But what you're talking about is, well, there's sometimes in these systems, there's human behavior. It's something that is somewhat unpredictable. And you need to add some kind of probability, right? So probability, likelihood, and that likelihood may or may not change over time, a bit like how humans evolved, right? Like little toddlers, they barely walk, they get more information, they grow, they change, the world around them changes, and as a result, they're adapting to their new situations. Is this kind of like the whole philosophy around Bayesian inference, that you can take any complex situation scenario and based on its surroundings have the natural laws, physics, control algorithms evolve in such a way that it's more robust? Is that kind of the philosophy, or am I simplifying this too much?
No, I don't think that you are simplifying that too much. I would just add a bit on that. Is basically Bayesian inference is a principled way of handling the uncertainty, which is induced either from your imperfect beliefs or some imperfect sensors or some imperfect assumptions about the world and basically also about the world itself, because modeling everything is relatively hard. It's,
Yeah.
I would say, it's rather impossible. So Bayesian inference allows you to ground yourself by acknowledging that you can't know everything and you need to keep updating your beliefs in the presence of new data. And it indeed applies to control and other parts of what's so-called AI, right? There's a notion of Bayesian AI, which we can talk about as well. But the whole process is indeed, as you said, is basically, well, start with some belief, then collect new data and update this belief. So, and these beliefs are represented by probability distributions.
So can you walk me through a concrete example? So you already walked me through what you did at your university in Japan, but can you give me another example that really grounds this concept of why is it so useful?
Sure. I'll just give you another example by basically explaining why I've joined TU essentially. So I've been looking for basically places where I could study this Bayesian inference and where I can actually build up the agent that can incorporate the uncertainty and adopt in real time, preferably. And then I've stumbled upon this position at the University in Eindhoven. And the idea of the project was about developing the Bayesian inference for personalized hearing aids, and which very much resonated with the challenge I had faced previously during my master's, but hearing aids are operating at much higher sampling rate. And then the problem is the following there. So I'll try to walk you through that. So hearing aids are awesome devices, right? They really help to mitigate problems with hearing patients. And they work perfect as long as the environment is not changing. For example, if we're now having a conversation, while the hearing aid would be working perfectly, but then what happens is you go to the bar and it just basically breaks. It annoys you. You don't hear anything anymore. And while having the conversation with your partner, right? So what happens usually is that the hearing aid patients, when they encounter this kind of the problem, they go to an audiologist would try to tweak the hyperparameters, but that's really hard because the situation that the hearing aid patient experienced, it's gone. And basically replicating it in the controlled environment, you can imagine that's almost impossible, right? So you can't really match exact that acoustic environment that kind of induce that, frustration from the hearing aid patient. So what happens is that if audiologists succeed in tuning that, that's great. But if not, what happens is that this hearing device will be taken from audiologists to engineers. Engineers will work on this for like a few weeks or months, right? And then eventually, so this whole design cycle, this whole process of fixing the bug or actually fixing this hearing aid would take a year or something. And you can imagine that by the time it is fixed, it could be pretty much irrelevant for the hearing aid patient because they are already frustrated, right? So it just ends up in a drawer. And then my professor, like my supervisor at Bias Lab, so he had this idea of actually incorporating the Bayesian inference in a specific type of it to apply for personalized hearing aid. So what we basically decided to do is to place a so-called agent in the hearing aid, which would be scanning the environment of the acoustic environment, and it will provide the intelligent algorithm settings for the client, for the hearing aid patient, by tracking basically the preference of the hearing aid patient and the acoustic environment. You can imagine that the acoustics are always changing, that people are not staying at the same acoustic environment. So you need to obviously model this like high level of uncertainty while you're at the bar or where you're at the metro station and so forth. But you also need to have this feedback from the hearing aid patient and the hearing aid agent. And the idea is that this agent, through time, it would learn what is the preference of the patient given the acoustic context. And that's where kind of the Bayesian inference and the particular instance of it shines. And that's essentially was the topic of my PhD.
So let me see if I get this straight. So the idea is if you can use mathematics or probability in such a way that you can change the operation of a real life system to cater for uncertainty, then you can actually design more robust, more personalized devices. And this probably holds true on pretty much everything that we interact with on a daily basis, which people probably throw the term AI at, but this sounds like a much more mathematical way of doing things as opposed to just throwing data at a problem, hoping for the best result. Is that kind of your reasoning?
I think that's a great summary, Garrett. Yes. Yeah, you've mentioned this AI, right? It's just funny that there's an interesting fact about that most of AI researchers, they often avoid using the term AI, right? Due to its broad and very often misleading nature. So I personally prefer like more specific terms like machine learning, but we can stick to AI. I guess especially now after the rise of GPT, this hype is unstoppable. So let's roll with it. Yeah.
Indeed. So I guess the term AI is abused and misunderstood by everybody. And there's subsections and different types of machine learning and different algorithms. And if I understood correctly, this Bayesian inference, this is a category of machine learning, but you also called out earlier something called Bayesian AI. So is this a specific type of machine learning? Can you kind of give me a 10,000-foot overview of how does this fit into the AI world?
That's actually very easy because basically Bayesian AI or like Bayesian artificial intelligence, it's basically any sort of AI system that utilizes Bayesian inference, the same statistical method that I was talking before. So again, in Bayesian AI, this just uncertainty is represented probabilistically. That's the main idea. And that allows for more nuanced decision making and like reasoning in different uncertain dynamic environments.
But does this fall underneath the category of reinforced learning?
I think here it's important to separate a few things actually. So first of all, I've just spoke briefly about Bayesian AI, but it's not something like really at the press at the moment. So the thing is that you're right, there is like a notion of reinforcement learning, and we are trying to opposed to that with something we actually call the first principles AI. And I will just try to connect these dots actually. Let's, for the sake of this podcast and just for the clarity, focus on the first principles AI rather than Bayesian AI, because Bayesian AI is way broader, and maybe it would be better if I actually speak about what is the first principles AI first, and then contrast it to the reinforcement learning, if you don't mind. So basically what first principles AI does, it's a just type of AI that focuses on the specific technique which grounds in the fundamental principles of physics and biology to develop adaptive systems. And it's interestingly enough that this type of AI, first principles AI, it's at the core uses the Bayesian inference. So this first principles AI is basically seeks to understand the intelligence through the lens of the self-organization in biological systems such as a human brain. And there are many kind of research going on showing and has been done actually showing that our brain essentially is doing Bayesian inference. And here it's important to note something about first principles AI in general, right? Some people actually imply a different thing, which is called, and perhaps you've came across it while preparing for the interview, is physics-informed AI, and where basically the physical laws are integrated into the training process of AI models. That's something like SkyML is doing actually. And typically they incorporate the differential equations into the optimization functions. In our case, when we talk about first principles AI, the research I've been doing in the laboratory or now at Lazy Dynamics, we imply something else. We use first principles AI to explore how the agent learn, explore, and adapt to changing environments by emulating the process observed in biological systems. It's very interesting that you've mentioned reinforcement learning, because reinforcement learning also has this idea of basically acting in the environment, collecting some data, and then update your parameters based on the feedback from the environment, which is usually induced by the reward function. In the reinforcement learning, there's a lot of research being done on how to craft this reward function, and there are like thousands of different reward functions out there. There's also, of course, notion of surprise Bayesian reinforcement learning, right? but the core difference between the first principles AI and reinforcement learning is that in the first principles AI, we're taking probabilistic approach. This is the first thing. And another thing is that there is just one optimization function. The point here is that in first principles AI, we don't handcraft the reward function, because the reward function is there. It's basically the reward function, as we term it for now, in first principles AI, it basically constitutes how the agents learn and perceive and act upon environmental data streams.
So let me see if I understand this correctly. In my mind, I have this mental model of a use case of reinforcement learning is, let's say I have a robot and I want it to walk, right? I want to train it to walk. And I say, okay, to reinforcement learning, this robot, it walks and one of my rewards is the further it goes, the better that the reward is. So it changes the control algorithms. And I say distance all of a sudden is a criteria. But then you could also say direction, speed, and you start mixing and matching physical constraints into this funky reward thing that may or may not make sense, but it is almost an art to figure out what is the ideal reward function for this reinforcement learning to work, right? And you might simulate this with a computer and you might say, okay, the laws of physics apply to the robot, but actually that's just the laws of physics that I'm dealing with. But what you're saying here with the first principle AI is this reward function, because it's unknown and there's not a strong science of what the ideal way to do it is, with probabilistic approach, you are able to get that for free, and therefore you can design systems in a more robust, clearer way. Is that it?
Yes. So in short, yes, you're right. You've just pinpointed a very interesting differentiator of first principles AI and reinforcement learning. The key in the first principles AI is that we're not explicitly giving the reward to the agent when he's doing something right or wrong. So basically how it starts is that all agents are defined within the probabilistic model. So we frame every agent that operates in a certain environment should have a good model of its environments. But the core here is that once the agent is equipped with this model, which constitutes its beliefs on how the world evolves around him, then you can say to an agent by means of constraints on these models that you want this agent to go somewhere. You don't say, you don't encode it in the reward function, but you basically say, okay, I want our agent to move from this state to another state. And then you say, okay, do Bayesian inference. So I've said that in the Bayesian inference previously, that the whole idea is to get this posterior distribution, but you can actually rephrase it in the form of minimize your evidence. And what we mean by that is the agent seeks for the actions and seeks for the paths, like in the example of the robot, right? Which path I should take that will maximize my evidence over the model. So
yeah,
in principle, it's quite different, right? So you don't really encode, you don't have this very explicit reward function, but instead you're actually saying that the agent should operate in the probabilistic setting.
So I'm beginning to see now that there's a fundamental difference. And if I understand correctly, you took all of this knowledge, research, theory, and that's how you created lazy dynamics, right?
We are like really on a very ambitious mission to revolutionize this development of these adaptive intelligence agents by building a software engine that streamlines the entire process. So the thing is that these agents that rely on the first principles AI that we've discussed, if you were to build them right from the scratch, you would have to endure tedious calculus and very challenging programming. And this makes prototyping and development time consuming and like prone to errors, especially as projects grow and the more team members join in, it becomes really not scalable and not maintainable for most of the cases. And to tackle this problem, we first developed, while being at the university, at the laboratory, we first developed this open source toolbox called Arix-Infer, which consolidated many years of research and engineering from our lab. And then we took this kind of way, it was open source. And then we said, okay, we see that there's quite some interest growing in the field of first principles AI because, well, the generative AI and other, let's say, purely deep learning based methods, they aren't meeting the requirements of the systems that must operate in the uncertain environments. And then we said, okay, look, how about we take this Arix-Infer and make it Arix-Infer Pro by basically making a professional toolbox that would streamline this development.
So tell me more about this Arix-Infer. First of all, which programming language did you use to program it?
Yeah, Arix-Infer is based on, it's programmed in Julia. That's our core language in BioSlab, in the laboratory where I was doing my PhD, and now obviously at the company.
So Albert, this Arix-Infer, tell me more about it. And can you ground this with a concrete example? And maybe what I'm thinking in the back of my mind is, how do you actually specify this model? And can you explain to me how you're breaking everything up into small components?
Arix-Infer is a Julia package which was essentially designed to automate the Bayesian inference through something called reactive message passing on factor graphs. So there's quite something to unpack here. Let's assume that Bayesian inference has been covered. First of all, what is a factor graph, right? So every agent is encompassing and consisting of a generative model that describes the environment around him, that describes the action space, like what the robot, if we are talking about the robot, what the robot can do, where it can go. And also it describes the dynamics of the robot. And it's also, it's, you could see that there are like several components already up there, right? So you can think of, if we're talking about the environments, right, how the robot will sense this environment. If we talk about the dynamics, okay, is it a wheeled robot, or if it's bipedal, does it have joints? So this model, this probabilistic model that describes the agent is usually very well factorizable, right? Because while you could, I think it's pretty obvious that the sensory data from the vision doesn't have to be explained in the same functional dependency as the joints. So you can actually split up the very big function consisting of many variables into the product of essentially many small functions. And these can be translated into the factor graph that basically describes this kind of, it has a sparse representation of the dynamics of the agent. So, and then that is it. So this factor graph it's a graphical representation of the probabilistic model of the agent. Now, there is something called message passing. And why is that? Is because message passing turned to be a very computationally efficient method of employing Bayesian inference. So at the core, as we said, Bayesian inference, or I actually forgot to mention an important aspect of Bayesian inference while being like a principal way of updating your beliefs. The problem with Bayesian inference is it is notorious of being extremely computationally expensive, right? So it's really hard to perform the Bayesian inference. It's a very heavy computational load on your computer. So we cast this probabilistic model into the factor graph, and then we perform the message passing. And message passing basically allows you to scale and reduce the computational load of Bayesian inference. Now, message passing by itself is, of course, not a new concept. Message passing was, I think, firstly introduced around 1980s by Judah Pearl. And what sets Arix-Infer apart from this message passing in general is the reactive programming or reactive nature of Arix-Infer, which in our opinion puts the message passing on a totally different level because it does the computations only when the information becomes available. So let's say you have a sensory data, right? You have let's say a microphone, and then there is no point of doing the calculations unless some data impinges on your microphone, right? So why would you spend the computational resources while there is no information available? But it also applies not only to the sensory information, it also applies to the dynamics. For instance, if there is no input to your joint, then you don't compute anything, right? You don't update your beliefs. So this reactive nature of the message passing allows us not only to save computational resources, but it also allows us to do these computations very effectively, like only when it is needed, when it is triggered locally.
Okay, let's say I'm a future customer of yours. Walk me through this Arix-Infer Pro kind of approach.
So I think where Arix-Infer Pro is shining is that when you're working with the resource constrained device and you have to operate with the fluctuating resource power. So basically, when you drive a car and let's assume we are on a highway and there are no cars around. Let's also recall that I think that the power consumption of our brain is around 20 watts. And say we are driving, we're not spending too much resources because there's not many cars to track, but then suddenly cars start to appear one after another. And then let's say there's a truck in front of you. So you basically have to start tracking all of these cars, all of them, while being resource constrained, right? So you can't allocate more energy, right, from your brain. It's there, it's just 20 watts. So you would have to basically spend, let's say, 4 watts to the truck, 2 watts to the car, I don't know, 0.5 watts to look at your phone, right? Sometimes. So this kind of stuff. But you don't have a luxury, let's say, of just magically allocating some new resources to track the cars around. Now, that's what Arix-Infer tries to, with this reactive approach, it tries to achieve. Basically, we say, all right, we have a system which is resource constrained. It operates only with a certain amount of power, of memory, and we will only react and we will allocate resources when it is needed. When the new car appears, Arix-Infer will spend more computational resources into tracking the car, right? Because if we are talking in the realm of self-driving cars, for instance, like the main goal is actually not to hit the car. So you would actually have to spend more computational resources on the cars which are next to you, but perhaps not very much caring about the cars which are on your back. And in a similar way, RX Infer was operating on applications for hearing aids. So hearing aids, you can see that it's like even like the computational resources are even smaller. It's like really resource constrained, and you have to do this basically updating very fast.
Then I guess the hard part then is this creating this model, right? So I think, okay, so if I'm an electrical engineer and I look at the physical principles, right? If I look at a robot arm, I have two joints, right? I can write down the equations, joint one, and there's a double pendulum, there's a second joint, and I can apply the laws. And the more joints I add and the more dimensions, the equations get longer and longer, but effectively I could write down the equations. I could also use, I don't know, tools like MATLAB, Simscape, where I connect blocks and then I run simulations, and then underneath the hood, the equations with ODE solvers, this is also taken into account, right?
Yeah.
But effectively, all of these cases, they're always using all the computations of all the joints at every point in time. And what you're saying, if I understand you correctly, by allowing Bayesian inference, you can also do probabilistic behavior that changes and adapts over time, where you can focus based on a new scenario where you need to put more pressure on a joint A or joint B based on new information, and that can be described mathematically. And even though computationally expensive, this bit of the magic sauce that you've come up with is this message passing that has existed for many years, but you developed it in such a way that it becomes now a reality and can be applied on small computation. Is that kind of where this all kind of comes together, that you said there's a better way of doing things? Is that a good summary?
Yeah, I think it's a perfect summary, Garrett, and you're right on the spot. The thing with RX Infer and the example I just gave to you, and with these fluctuating resources and resource constraints and the power constraints, I think it's where we are going. I don't think that we are there at the moment, but it's a very long journey to take. And that's actually partially relates to this problem of actually translating research into the product. Right. So that's true. And that applies, I believe, across all academia, right? So you have all these research papers, which are at the best are reproducible, but it's always also sometimes a problem, right? You just download the paper and then all of a sudden the code doesn't work, because there is quite a problem with, I would say, programming etiquette in academia. But nevertheless, that's where we are indeed going, and I think you summarized it pretty well. So, and you've touched upon the model, right? So I'm all the time like referring to some model,
yeah,
and then this model is there. The bitter truth is that the model is usually not known, but it's not. I would argue that it's not like it's never known. There is this idea is that we don't know anything about our model, but that's actually not true, right? So some prior information is always available, because you're solving a problem. You're solving a particular problem, so you know something already. And then for the parts where you don't know, you can actually compensate it with Bayesian inference, because you can actually handle this uncertainty. And when I say that, you can have not a perfect model. You can say that, okay, I have many nonlinearities, but maybe I can linearize some part and then compensate it with a noise term. So you can always construct a model and start from something. And then what is nice about RX Infer is that you can iterate very fast through this model. So you don't have to care about inference, right? This inference is taken apart, so it's taken away. So we've coded it up. So the person should just specify the model. It's like usually one or half a page of the code. You iterate through this model, you try different things, and then you just see right away, okay, how your agent is operating.
I think it's very inspiring what you did. But maybe to take another step back, because you said this was programming in Julia. Why did you do Julia or not, I don't know, MATLAB or Python or C or Rust? Walk me through why Julia.
Sure. Can we take few steps back?
Okay, sure.
So because my journey with Julia began in like 2018 when I actually applied for BioSlab. I knew that lab was using Julia for coding, and that language which I've never encountered before. And I must say that I had quite some touch on programming languages by that time. So I had to prepare for my PhD. So I decided to rewrite my Python code for this driving aid project into Julia. And luckily, one of the core algorithms that I used, which was extreme gradient boosting, it was already rewritten in Julia. It was basically a very smooth translation. And I must say that I wasn't initially sold on Julia because the syntax reminded me too much of MATLAB and a language I wasn't particularly fond of. But despite my reservations, I reluctantly embraced Julia for the sake of my PhD. So especially since it was the preferred tool in the lab. And actually, at first, I secretly continued coding in Python because my initial demos were also in Python, and I simply couldn't let go my trusty PyCharm editors. And yeah, however, my professor, let's put it, he encouraged me to use Julia, so I gradually shifted my focus. And I began with coding in Julia and even contributed to packages at fornilab.gl, which was like the first iteration of this message passing implementation of Bayesian inference. And of course, the journey wasn't without its challenges. Like Julia, so it was 2018, right? So Julia, like early versions, lacked user-friendly tools, and troubleshooting errors could be quite discouraging. You probably know this fancy stack traces sometimes you get. But I persevered basically, and I was driven by this necessity of using Julia for my research. And over time, Julia stabilized and improved, and I started to appreciate its advantages, especially in its efficiency in computational tasks, right? Like if we talk about the performance, Julia is like, it has exceptional speed and it's ideal for scientific computing and data analysis. It's really like, it's often a rivalry to compiled languages, right? And then syntax is great. I fell in love with it because there is a notion of types, right? And then if you are coming from C or C++, you really get to appreciate it very fast. Then there's multiple dispatch, right? It enables like this code reuse, and it's really cool. But my favorite thing in Julia is this metaprogramming, which I must say something here. Actually, I'm not doing metaprogramming in Julia by myself because it's all done by other people in the laboratory or our startup. But in Rx-Infer, the way we define the models, the way we define these probabilistic models, it's so much similar to how you would do it mathematically. So this notion is really, so you basically metaprogramming within Julia allows you to write your own domain-specific language, which is really sweet. So, and that's basically, I'm now sold on Julia. So it's a great language. I program it. Most of the time, I would say 90% of the time I program in Julia, whatever, like simple task and hard task.
Maybe to just double click on that. So when you say metaprogramming, maybe not everybody in the world knows exactly what that means. Can you describe to me what is exactly metaprogramming in the Julia context?
I'm definitely not the best guy to be asked about it. They're like really hardcore metaprogrammers within our laboratory. But essentially, like in simple words, it's basically like it's a technique essentially that allows you to specify the computer program that will be treated as another program. So just to give a concrete example in Rx-Infer, right? So when you do a model macro, so you do add model, and then that language that follows, it's not per se Julia language. It's actually like our own language that allows us to have a very high level abstractions on how our basically agent is constituted, in the sense that you could write. So for example, in Julia, you cannot write actually X tilde normal, which would say that the X is drawn from a normal distribution. But through metaprogramming, you can actually introduce this ability for Julia to parse it properly. So you could, and that's really eases your kind of programming experience like a lot.
So maybe just to make sure I understand. So the idea is Julia super fast, as you called out,
yeah.
But it feels like one of the things that got you hooked was the expressivity as a mathematical background, that you could change your mathematical domain knowledge in such a way that it maps nicely into a programming language, makes you productive. And metaprogramming is a way to achieve that. That's why you use Julia. But maybe you can tell me a little bit about your journey of some of the war stories that you went through in embracing Julia, because I think that's worthy for people to understand that often the first contact with a new language, you get this, this is not for me feeling. But then if you stick around long enough, eventually you see, oh, this was the best thing ever. And you're an example to a point that you created a company around this.
Yeah, that's true. Like we used to joke that like our love towards Julia could be also explained by Stockholm syndrome. Like you just had to do that, and then eventually you grow to love it. In all honesty, I actually don't have any like battlefield tales to share about that. It was really It was a hard journey in the sense, as I said, right in the very beginning, it was hard to use I've started when Julia was 0.6, and thanks to core developers, the breaking changes weren't coming every day, but they were coming, right? So it was really not the troubleshooting was hard, and eventually, the thing is that when I was writing some code in Python, like secretly, and sometimes translating it to Julia. So at some point when my computations, when I had to write down this Bayesian inference within Python and essentially compute the integrals, I realized that I cannot beat Julia. There was just like nothing I could do to beat Julia in terms of speed. It was so fast. And then I was really impressed. I was obviously reluctant to code these heavy computational operations in C, but I've tried out Python, obviously MATLAB, and yeah, Julia was just unbeatable. So I've decided, okay, so that's time to switch and commit. And since then, yeah, we've started to code only in Julia, and then yeah, we've started to get more and more people, and now there's a whole laboratory, I think like more than 15 people, and everyone is coding in Julia, and I think pretty much enjoying it.
So maybe then to just talk a little bit more about the RxInfer. So typically in the Julia community, to the best of my understanding, people are encouraged to write smaller packages and have more of them, right? So as opposed to having one gigantic package that does everything, you have lots of smaller ones. Are there related packages which are worth calling out associated with the RxInfer that they relies on either upstream or downstream?
Yes, actually, yeah, great question, Garrett. And actually, that's what we adopt as well, right? That as well as in the Julia ecosystem, people are trying to basically split kind of use this divide and conquer approach and split their big packages into smaller packages. And that's what we did as well. So when I'm referring to RxInfer, I'm actually referring to the whole ecosystem of several packages that embodies RxInfer. RxInfer essentially, it consists of, I think, 5 packages. So there is Rocket.gl, which implements the reactive programming, essentially. So it's this type of a paradigm which we use underneath. Then there is GraphPPL.gl, and GraphPPL is when I was referring to the sweet spots of metaprogramming, they're all in GraphPPL because it allows you to write down your model mathematically by using the notion of probability distributions, and then it will cast it to the factor graph underneath. So that's what GraphPPL does. Then we have reactive message passing.gl or reactive np.gl. That's actually how it all started. So this was the first package which was implementing all of it. And then it started to split to smaller pieces. Reactive message passing or reactive np.gl actually implements the computations. So it's something that computes the messages, it computes the products, and actually perhaps products are also now shifted to another package which is called exponential family.gl. All right. And then all of it fuses into RxInfer .gl. What RxInfer essentially does, it implements a function which is called infer. So you have all these components coming from different packages, GraphPPL, Rocket, exponential family.gl, and reactive np.gl. And then all of it kind of fits into the one package, RxInfer, that allows you to call the function, so specify the model and call the function infer.
So given your journey that you went through, do you have any advice that you'd like to give your younger self? If you could go back in time and talk to the teenage version of yourself, what would you actually tell the younger Albert?
Yeah, that's perhaps the easiest question you asked me today, because I have it in my mind is that I would definitely go back and advise not to get married when I was like 22 years old, right? And another one would be like to pay closer attention to variational calculus during my bachelor. That's 2 advices I would definitely give to myself. But to be honest, like joking aside, reflecting of what advice I would give to my younger self feels like it feels a bit like suggesting that I'm dissatisfied in some way where I'm now, and I believe that, yeah, I could have a better place if I had known certain things. But however, it's not the case for me. The truth is that every up and down, like every struggle, which was during the bachelor's and obviously during the PhD, it's shaped me into what I am today. And yeah, from my journey to Bias Lab, like competing my PhD, to founding Lazy Dynamics, like each of these challenges really contributed to the growth and led me to the place where I'm content. So I wouldn't particularly, they give many advices, but yeah, perhaps, I mean, maybe one I would give to myself, to my younger self, is that it's okay to doubt yourself. Like if I appreciate it like earlier, that would be good. Because yeah, you hear all these motivational speakers like telling you, yeah, I should never doubt yourself. But the reality is that doubts are inevitable, and in fact, they're a crucial part of risk assessments. That's actually why the Bayesian inference is so cool. So that, because it really gives you a principled way of doing that. And the key here is just not letting those doubts control you. Instead, that's what I do. I just use them as challenges to overcome, opportunities for growth.
Nice. Okay, you've definitely got a very interesting story, and thank you very much, Albert. If people want to reach out to you, what would be the right way?
There's email available on our website, lazydynamics.com. I'm also a part of the Reactive base, which is our open source organization revolving around RX Infer. You could reach me out through discussions on GitHub, or simply just writing me a message on LinkedIn.
This is a great place to stop this episode. I hope it triggered your curiosity in some shape or form of how MATLAB, Python, or Julia are actually used in the real world. If you did find it interesting, just subscribe in your favorite podcast player. And while you're at it, write a review, as this will help the podcast going strong. In addition to that, don't be shy, share it with a couple of friends, as who knows, one of them might be a future guest on Inspiring Computing. Thank you.